So whatever X is on this ring, this is the directing group. It has an effect on the ring, and it tells Y where to go. So X says, all right, Y, you are going to go in the para position, all based off of my properties. So all based off of the properties of X. X has an effect on the ring. It changes the electronics of the ring. So it tells Y where to go. So if X was an Ortho-Para director, all right, Y would go, you would technically form two compounds. You form the ortho compound and you form the para compound. Technically, you do not form equal amounts. You form more of the para. Okay, so maybe like 70% para and 30% ortho. It also depends on X. The larger X, if X is very large, okay, then it's hard to actually attach Y groups at the ortho spot. It can only go at the para spot. Okay, so technically your para forms more, but if Y is pretty small, you can get more of the ortho compound, but you do form more of the para. All right, if X was a meta-directing group, if this was a meta-director, when Y is reacted on there, you exclusively get the meta compound. Okay. Now you might get small amounts of Ortho-Para, but we're talking less than 10% of Ortho-Para. About 80 to 90% of it is going to be the meta compound. Okay. Let's not worry about the percentages. If you want to make the para, you just assume that you can isolate out the para compound. Okay. So let me show you an actual real life example. All right. So if you take phenol, we've learned that this is called phenol. And if you add nitric acid and H2SO4 as your catalyst, this is a nitration reaction. Remember, this is one of the reactions that we learned in the last section. All right, so I'm going to draw all three compounds, the ortho, the meta, and the para, and I'm going to give you the amounts of each. Okay, you form about 35% of the meta. I'm sorry, of the ortho, right? You get about 70% of the para, and you get about 5% of the meta. So you make, that doesn't add up, sorry. This is 60%. 60%. Okay, so you do actually form a little bit of the meta, but it's such a small quantity. Notice you kind of form a little bit more of the para, and you do form the meta. But basically, an OH group is a Ortho-Para director. Okay, so that's what you're going to get more of. All right, another example is if you have a cyano group, do the same reaction, H2SO4. So you can get the nitro in the ortho, or you can get the nitro in the meta, or you can get the nitro in the para. All right, your mixture, you get about 80% of it is the meta. You get about, in this case, you get 17 in the ortho, and you get 2% of it in the para. And that's because the cyanide group, believe it or not, is actually a small group. It's a linear molecule. So you technically have two possible sites of the nitro. So in this case, you get a little bit more. Let's not worry about Y and all that stuff. Just realize that the CN group is a meta director, and you get mostly of it in the meta. Okay, so how do you know if a group is an Ortho-Para director or if it's a meta director? I'm going to give you a little secret. It's a little secret I've learned along the way. I don't know if your book talks about it, but I am going to give it to you. Okay, Ortho-Para directors. There are two types of how you can tell if it's an Ortho-Para director. One is it is an sp3 carbon is directly attached to your ring. Directly attached to ring. All right, so if you have an aromatic ring and you have a carbon and it's sp3, it does not matter what's at these positions. If it's hydrogens or other carbons, this is an ortho-para director. So if you have a methyl group, all right, if you have an ethyl group, isopropyl group, tert-butyl group, it doesn't matter what it is. If it's an sp3 carbon directly attached to your aromatic ring, that is an ortho-para director. The second class is if the atom attached to the ring has a lone pair. It is an ortho-para director. Okay, I'll give you a generic example. So you have an aromatic ring, you have whatever X is, and it has at least one lone pair. All right, so like the OH example I gave you. All right, phenol. Well, there are two lone pairs. That's an ortho-para director. If you have an sp3 nitrogen, nitrogens have lone pairs. Halogens, if you got a halogen there, those have lone pairs. All right, amides. All right, well, an amide is a nitrogen, so we already talked about nitrogen. So if your group has a lone pair next to next to the aromatic ring, it's an ortho-para director. Or if it's an sp3 carbon, it's an ortho-para director. Those are the two main categories of ortho-para directors. Meta-directors are very easy. Meta-directors, right? If the group attached to the ring has a pi bond, then it is a meta-director. It's very simple. You get an aromatic ring, all right? And if you have a pi bond, it doesn't matter what any of those groups are. Notice I have a double bond. It could also be a triple bond. So the nitrile case, we saw the nitrile, that's a C triple bond N. Okay? If you have a pi bond adjacent to your aromatic ring, or the atom that's directly attached to the ring that has a pi bond, it is a meta-director. So examples are anything that has a carbonyl attached to it. So here you can have a carbon group, you can have an OH group, you can have a nitrogen group, you can have whatever, all right, whatever the group is. Nitro groups, this is the Lewis structure of a nitro group. All right, notice this nitrogen doesn't have a lone pair in this case, but it has a pi bond. So nitro groups are meta-directors. Okay, sulfonic acid groups. We've learned how to make sulfonic acid groups. Those have two pi bonds. That's a sulfonic acid group. All right, as a side note, notice your sulfur is more than an octet. It comes from the expanded shell rule. For those of you that took 111, you learned about the expanded shell rule. Things in group 3 can have a d orbital, so they can have more than an octet. Not important, but in case you're wondering why, that's because of the expanded shell rule. All right, but just to go back, just to review, ortho-para directors have lone pairs or are sp3 carbons attached to the ring. Metas have pi bonds. Could be one or two. That's how you can determine how it's going to do a substitution. So let's do a problem. If I were to give you this compound, CH3, and said, all right, let's do a Friedel-Crafts acylation on it with, let's say, isopropyl chloride and aluminum trichloride. Why don't you draw? Well, first determine, is this going to go ortho-para or is it going to go meta? I'm going to stop it, and then you can figure out what the product should be. All right, so notice the answer is ortho-para. All right, methyl group is an sp3 carbon, so that means it tells the isopropyl chloride you are to go either at the ortho position or the para position, because I am an ortho-para director. That's where I'm directing you to go. All right, in reality, you'd probably get more of the para, but you would still get some of the meta, but that's not important. Let's do another one. H3, and what reaction? Let's add chlorine to this. All right, again, I'm going to put on pause, and you draw what the major product should be. All right, so notice it is the meta product. Why is it meta? Because I have a pi bond directly attached to the aromatic ring. So since I have a pi bond directly attached to the aromatic ring, that means it is a meta director. All right? Makes sense? If it doesn't, will go over it, obviously, more in class, but that is pretty much how you determine meta directing groups and ortho-para directing groups. All right, 5.7 we're going to skip.